Hello everybody. In this video I'm going to show you some of the terminology, graphs, and equations of hyperbolas. Here's a picture of how all of our conic sections arise from the intersection of a plane and a doubly infinite cone. These pictures don't necessarily help us graph or write equations or find any characteristics of the conic sections, but they're pretty cool to look at. The set of all points or locus of points definition of a hyperbola is pretty similar to that of an ellipse, except the constant sum is replaced by a constant difference. So we want the set of all points such that the difference of the distances from each point to the two fixed points known as the foci is a positive constant. So what we're going to get is a picture that looks like this. We're going to have, let's draw two focus points, and then we want all the points that when we take the difference to those and subtract them, we're going to get the same number over and over again. What that ends up looking like is two sort of curves that are known as branches that go in opposite directions from each other. It's worth noting that these are not parabolas. They don't have that same shape, and we're going to look at that a little bit more in a minute. But why this ends up working out is, let's say we look at that point. It's a really easy point to look at, actually a special point that we'll talk about for vocabulary in a moment. But if we take this distance and subtract them, we're going to get a number. Now, if we take the point on the other side, that sort of corresponding point, we get the same two exact distances, except they're swapped. When we take the difference there, then we're going to get that same number, as long as we take the absolute value. And when we're dealing with distances and differences, that's okay. So if we take a look at another point on here, the reason the difference ends up being the same is what's happened is this distance and this distance have both increased by the same amount in relation to the distances that we saw before. So the further you spread out, what's happening is the distance here and the distance here both increased by the same amount, so their difference ends up being constant. Our hyperbolas that we're going to draw are going to have focus points that are always horizontally or vertically oriented in relation to each other, so they're not going to be tilted like this. And that will allow us to actually write equations for them. Not all hyperbolas have to be like that, but all the ones that we are going to see will be. We're going to start understanding how to graph hyperbolas by looking at this very basic hyperbola equation. As we continue to build, you'll notice similarities to the equation of an ellipse, with the exception of the minus instead of plus. Let's start by looking at the x-intercepts. If y was 0, then x squared would equal 1, and x would equal 1 and negative 1. If x equaled 0, negative y squared would equal 1, leaving no solutions, thus no y-intercepts. As mentioned before, the branches of a hyperbola are not parabolic. In fact, the further you move to the right and to the left, the straighter the branches become. All hyperbolas have two asymptotes. This particular hyperbola has asymptotes of y equals x and y equals negative x. If we draw these in, I'm not going to draw them dotted at the moment because my app doesn't allow that very well. But if we have the branches go to the right, they will get closer and closer to these asymptotes. If you want to understand why this makes sense with the equation, if you imagine numbers that make this equation true, think about, for example, x equals 10. If x was 10, 10 squared would equal 100, and y would need to be either the square root of 99 or negative square root of 99 in order for x squared minus y squared to equal 1. The further you go off to the right, the closer x and y would have to be in order to make this equation true, meaning x equals y, or y equals x, would be an asymptote. Similarly, y equals negative x could be an asymptote. While the hyperbola itself is just what's pictured in red, the asymptotes are very important parts of that drawing. Another part of the drawing that is very helpful in drawing more complicated hyperbolas is an imaginary little box that extends from these points up and down to the asymptotes, and from where those intersect the asymptotes connected to each other. This particular box in this very basic hyperbola has from the center width 1 in either direction side to side and 1 in either direction up and down. Those ones connect back to the equation, similar to what we saw in an ellipse with the denominators. In this case, the denominators being 1 squared and 1 squared will tell us how wide this box is. As our equation changes, as our hyperbola stretches, we will be able to draw this box as a guide for the drawing of our hyperbola. And the key features of this box is that these points on the hyperbola and the asymptotes all connect to that box. The asymptotes go through the corners, and these spots on our hyperbolas touch the sides. In the last example, we used the equation to try and understand why the equation of a hyperbola is the way that it is. We saw intercepts and we saw asymptotes. The reality is when you draw a hyperbola, you're going to start with the box that connected all of those features. In this example, we just have a slightly different hyperbola equation where y squared starts us out instead of x squared. When you start drawing this hyperbola, you're actually going to start with the box that we ended talking about last time. When we see that these are divided by 1 squared and 1 squared, that's going to tell us that the box from the center being 0, 0 for now, goes 1 to either side in the x direction and 1 to either side in the y direction. When we draw this box is going to help us guide drawing our asymptotes. So it's kind of like we're working backwards from what we talked about on the last slide. We're going to draw our box and then draw our asymptotes. The difference in this equation with y squared being in front versus x squared is the intercepts. In this case, if x was 0, then y would be either 1 or -1. Whereas if y was 0, negative x squared equals 1 would have no solutions. This tells us when y squared is first that the hyperbola actually opens up and down instead of side to side. Ultimately, when you get practice at drawing hyperbolas, you will be able to quickly tell which way the hyperbola opens. You'll be able to draw the box depending on how much this has been stretched, and you'll be able to guide them with asymptotes that go through the corners of the box. I wanted us to try to understand the shape of a hyperbola from the locus of points definition and from an equation understanding. And so I've held off on some of the vocabulary because honestly, they don't all coincide with both. For example, the focus points didn't really come into play in our equation examples, and these points known as vertices didn't really come into play in the locus of points definition. But let's recap. There's a lot of vocabulary in these hyperbolas, and they're all important and all things you're going to be asked for in questions. So we've got these points where the branches turn around, known as the vertices, and those are going to touch the sides of the box, which are not drawn on this picture. We've got focus points, or foci, that are also going to have a connection I will show you in a moment. We've used the word branches. Branches in here are not labeled in this image that I stole off the internet. But we have a branch here and a branch here. Okay. These hyperbolas are very symmetric and they have axes. The axis, which in this picture are the x and y axis, but we will be moving our hyperbola shortly. The axis that goes through the vertices and through the foci is known as the transverse axis. And the axis that goes in between the two branches is known as the conjugate axis. Okay? A hyperbola has a center that's not technically a point on the hyperbola itself, which isn't super strange. A circle has a center that's not part of the circle. An ellipse has a center that's not part of the ellipse, but that center is an important part of the measurement. We also have asymptotes that we saw. Those asymptotes end up going through the center, which I didn't mention in the last example. And you can see already why all of this isn't drawn in one picture, because it gets really, really cluttered. But then we also have that box that we mentioned that goes from the vertices until we hit the asymptotes, right? So these boxes connect to the vertices and the asymptotes like so. The last connection we need before we start graphing more general hyperbolas and answering questions about their characteristics is the fact that the distance from the center to either focus point is the same as the distance from the center to any corner of the box. We're now ready to start graphing a little bit more general hyperbolas, ones that have been stretched. These stretches are very similar to those of an ellipse. The x squared term is divided by a squared, meaning that side to side in the x direction it has been stretched by a factor of a. Similarly, y squared is divided by b squared, which means in the y direction it has been stretched by a factor of b. What is going to help us here is the box that we saw before. Normally, the box would be 1 by 1 if the denominators were 1s. Since the denominators are a and b, that means side to side, we're going to have the box at a and negative a, and up and down at b and negative b. If we now draw this box, it will help guide our asymptotes, and it will help us place our vertices. Our asymptotes will always go through the corners of the box. And now we have to think about where to place our vertices. We can think in the intercept way of thinking about it that we did before. As you get more practice, you will come to find that because the x squared term is first, we just know that these are going to be opening side to side, and the vertices will be on the sides of the box, and the hyperbola will be opening side to side. All of this can be done without thinking about the foci, but the foci will be inside the branches of this hyperbola. And if you want to figure out the exact coordinates of these foci, we start by figuring out the distance from the center to the corner of the box. Once we know that, we apply that from the center in either direction, side to side, or if y squared was first, up and down, to find those foci. This is as easy as finding the hypotenuse of a triangle, because we know this distance is a and this distance is b. The next natural choice of variable is c, and so we use that for the distance from the center to the focus, and we have in a hyperbola that a squared plus b squared equals c squared. Be careful to remember that a squared plus b squared equals c squared is not true in an ellipse, just because of the difference of what we called a and b and c there. Here we have a quick example where all we've done is reverse the order of the terms, so y squared comes first and x squared comes second, but notice that a squared is still under x squared and b squared is still under y squared. So what this tells us is that from the center, we are still going a to either side of the center, and b up and down from the center. So we can draw our box, and we can use that to guide our asymptotes. Excuse me, sort of missing a little bit. That's okay. Let's draw our asymptotes through the corners of the box. Then the only thing that this is going to change is that we know that this one has y-intercepts, not x-intercepts. So if we plugged in x equals 0, for example, we'd be able to solve for y-intercepts or vertices at 0, b and 0, negative b. This tells us that our hyperbola opens up and down. But like we mentioned before, if we don't think about that intercept as plugging in an x equals 0 and solving, we just know that if y squared comes first, it's opening up and down. If x squared comes first, it's opening side to side. Finally, before we're able to do a full example, we need to think about transformations. All of our examples up to this point had center 0, 0. If we want our center to be at h, k, that means we moved it h either right or left. And so we need to find wherever x is in our equation of our hyperbola, and that could be either as the first term or the second term, depending on whether the hyperbola opens side to side versus up and down. But we would need to subtract h from x wherever it is. If we need the y-coordinate to be k, then we need to subtract k from y wherever it is in the equation. This does not change any of the geometry related to the box that we've been drawing. A is still the distance from the center to the sides of the box to the right and to the left. B is still the distance from the center to the top and bottom of the box. We can still draw the asymptotes through the corners. We can still place the vertices on the sides. Okay, let's finish up with one example putting all of this together. I'll make a separate video with more varied examples. But in this one, we notice that we have the general format of the equation of a hyperbola. We know that because of this minus, because both of the terms are squared, because it equals to 1. We notice that there's been some subtracting and adding from x and y, which tells us that this hyperbola has been translated or shifted. We see that they are divided by different numbers, which tells us we've got some different stretches going on side to side versus up and down. First thing that we're going to want to do is rewrite this with the denominators as numbers squared, because that's going to help us figure out and draw our box appropriately. So we're going to rewrite the 9 as 3 squared and the 4 as 2 squared. Okay. We know that because we have minus 1 from x, that the center x coordinate is 1. And we know that because we have plus 1 with the y, that the center coordinate is negative 1. It has been moved 1 to the right and 1 down. All right. The example asks us to sketch the hyperbola in addition to finding the vertices, the foci, the equations of the asymptotes. So I took this example out of a textbook, and this is typically the phrasing I see. But even if they don't say sketch the hyperbola, or even if the sketching the hyperbola comes last, I think it's the first thing that you should do. Even if they don't ask you to sketch the hyperbola at all, finding the vertices and the foci and the equations of the asymptotes is much, much easier if you have a graph to go on. So let's draw a sketch of this. Sketch meaning we don't have to be super accurate. We just want something to guide our thought process. So I'm going to label our axes here. We're going to place down our center. We're going to draw our box. We're going to use our box to help guide our asymptotes and place our vertices. And then we know some of the geometry of that box is going to help us figure out where our focus points or foci are. All right, let's start with the center. 1, negative 1. Then we have a 3 squared under the x, which means from that center, we've got 3 to either side to draw the edges of our box. 1, 2, 3 to the right. 1, 2, 3. 1, 2, 3 to the left. Then we have a 2 squared under the y term, so we have 1, 2 up and 1, 2 down. And I'm going to now draw a box. Okay. Now we have our asymptotes that go through the corners of the box and to the center. We can draw our hyperbola in now because we know that because the x term comes first, that the vertices are from the center directly on the sides of the box. We could actually write those vertices now. Makes it much easier to think when you have it drawn out. All right, so we could start answering questions if we wanted to. We have our vertices. Now hopefully it's clear at from the center. 1, -1, we moved 3 to the right, so that's going to end up being at 4, -1. And then the other one, 3 to the left, so that's going to end up being at -2, -1. Okay. The foci, we could draw those in, but it's going to be a little bit of a rough sketch at first. So if you don't feel comfortable placing them until you have a value, that's fine. We know that the distance from the center to the corner of the box is going to be the distance that we need to go from the center to the focus. We can calculate that, and I usually draw it sort of in a different location than I'm going to draw my focus points, just to not clutter it up. So I'm actually going to draw this triangle in like that. I know up and down is 2. I know side to side is 3. So we've got that triangle. We can now do the Pythagorean theorem and say 2 squared plus 3 squared, which is 4 plus 9, which is 13. So then this is the square root of 13. And so that means we're going to go square root of 13 from the center to either side. Because square root of 13 isn't a nice number, that's not going to be a perfect exact point, but we know that the square root of 13 is a little bit less than 4, a little bit more than 3. So if we go from the center over 1, 2, 3, and a little bit, we can roughly plop it down there, and that's good enough. We can, though, label it or write it down as they asked us to, that the foci would then be 1 plus the square root of 13, comma -1, and 1 minus the square root of 13, comma -1. Be careful that you don't just always add it onto the x coordinate. If this had the y squared term first, it would be up and down, and you'd have to add it and subtract it from the y coordinate. Finally, they ask us for the equations of the asymptotes, because we know a point that it goes through, and conveniently that triangle picture tells us that the slope of this is up 2 over 3, and similarly the other one is going to be down 2 over 3. We could write the equations of these asymptotes very easily using the center and those slopes in point slope form. If they ask you to write it in any other form, you could start with point slope form and manipulate from there. So our asymptotes end up being y minus the y coordinate, so plus 1 equals 2 over 3 times x minus 1, and y plus 1 equals -2/3 times x minus 1. Okay, that's a minus. All right, again, even if they don't ask you to sketch the hyperbola, I highly recommend sketching it before answering questions about vertices, foci, and equations, because it just helps guide your thought process.